Okay. All right, here we go. Hello. Okay, so today might be a little rough and kind of all over the place, but I had some emergency paperwork to sign at lunchtime, and we were running all over. But anyway, but I wanted to show you this. My daughter is just about to turn 2, and she already knows how to spell. So I wanted to show you this.
How do you spell your name? How do you spell your name? How do you spell Emma? Very good. How do you spell Emma? And then how do you spell Samuel?
So while you were laughing, I asked her, how do you spell daddy? And then how do you spell mommy? So that she knows how to spell. Okay. So let's go to just a little. Okay. So we have a new topic to cover today. But it comes from an old topic. So I've got some review questions, a picture here, some review questions. I want you to take about 2 minutes, but not yet. Just let me read them here. So you're going to answer, what does each vertical axis measure? How many functions here are represented? Identify each, be specific, as many details as you can identify about each of those functions. And then what is represented over here by the blue vertical line and all the blue dots? Those are your 3 questions. Take a couple minutes to talk through those 3 questions. Go. All done? Okay. Left vertical axis. Left vertical axis. Left vertical axis of the left graph. It's rate of change, right? Rate of change. Right graph, vertical axis. Oh, so the curve then is we often called it R, right? The curve called R, right? So then on the right graph, total accumulation, right? That is total, and we generically might call that Y, okay? So, how many functions are represented? How many functions are you looking at here? There are 2, 3, and 5. Okay, 4. All right. Anybody for 1? How many functions are you looking at? 3. There are 3 functions up there. How many functions on the left graph? Two are graphs. Those are two different functions, right? The first one is r, and what's the other one? Step. And is that step function is based on what? It's based on midpoints. You see that it's based on midpoints of intervals. Okay? So that we have the original red graph, it's our changing rate function. And then we have this the blue step function, which would be based on midpoints of the x interval. And then on the right, we have another function. What function is that? Accumulation. Specifically, what are you looking at when you're looking at that right there? Is it exact or approximate? Yes, so the blue dots maybe are trying to indicate that it's approximate. So is that a curve? Is that curved? If it's approximate accumulation, is that curved? No, it's a little, very small linear pieces, right? Very small linear pieces. I guess you wouldn't have known that. You might have just guessed that based on what's going on over here. Okay? And that was our next question. All right, so without this right here, you really can't know. These intervals are so small. Maybe that's exact accumulation. Maybe that's the piecewise version based on the step. Okay? So what's going on here? Question 3. What are you showing there by the blue line and dots? What's that? He said delta y's. Is that vertical segment showing delta y's? Oh, you're not sure. Penny likes it? Delta y's. Yeah, it's showing delta y's, each one from each constant rate of step. Okay, so for the first constant rate, K1, there's a corresponding delta y. And so that is that much accumulation. And then for K2, you've got the next little bit of accumulation between those two dots. Similarly for K3. So then what does this point represent right here? This point means what? That point means the total accumulation. For the current value of x. So maybe x here is about 4.2 or 4.1 something. And so this is 4.1 and what are we calling? We're calling it A. So A of, and what does A of 4.1 have to do with this blue line and the dots right there? What does A of 4.1 have to do with that blue line and the dots? Where does that number come from? Yeah, all the changes in y. So it's just the sum of all these changes, each one coming from a step and the delta x, right? So the sum of all those gives us the total approximated accumulation at this value 4.1. All review, right? All review. Okay. I don't know where we're going here. So we want to talk about another way to think about this. So far, what could y be? So like we said this was y, total accumulation. What are some possibilities for meaning for y? Speed. Is that right?
No.
Usually we think of speed as rate of change. So distance. What else? Height. Weight. Tax due. What else? Position. Okay, that's kind of like distance, yeah. Temperature. Have we almost finished the list? Are we almost done? No, we can spend 10 minutes thinking of quantities, right? So just amounts, quantities. Y means an amount. Y means an amount of something. Okay? And so we saw lots of different examples of amounts. So we're going to take a look here at an alternate understanding of integrals. We saw the integral calculated So for instance, this integral from 1, this starts at 1, so this is like a equals 1, right? To 4.1 of r of, let's say x, r of x dx. Is it a number or a function? That's a number. That's an amount of accumulation. What number is it? It's the, if this were the exact accumulation function, it'd be the y-coordinate of this point, right? And so this, for us, was, we were saying this calculates the exact amount of accumulation of some quantity from, as x changes from 1 to 4.1. So that might have been height, that might have been temperature, tax due, weight. Okay, so this is how we conceived of the meaning of integral. Okay? But there's an alternate understanding, and it actually, in the traditional calculus course, and for several years now, this alternate understanding has been the focus understanding. Okay? So let's take a look at what that is. So notice that, you notice over here, so this K1 delta x, this little bit of accumulation, here's K1. How can K1 be represented? It can be represented by the kind of like in the graph, the height of that step, right? See that? And what about delta x? That's this like little horizontal distance, right? So our rate is represented by a kind of a vertical distance in the graph, and the delta x, a horizontal. So K1 delta x kind of has a geometric meaning, kind of coincidentally has a geometric meaning. Do you see what it is? Yeah. Length, delta x is like width times height. So it's like width of a rectangle times height of the rectangle. So that K1 delta x can be kind of assimilated to be the area of that rectangle formed by the rate and the width delta x. Okay, so the area of that rectangle has the same value as our first bit of accumulation, K1 delta x. And then second rectangle, K2 delta x, right? Second, and then third rectangle, etc. Okay, so that integration is remotely related to areas of rectangles is entirely an artifact of the fact that we're graphing in rectangular coordinates. It's kind of like a coincidence. Because of the way that we graph, it just turns out that we're putting our rate this way, and we're putting our delta x this way, so kind of incidentally, or just an artifact of that, the way that we graph, is that this K1 delta x is kind of can be thought of as an area. Okay? But it's mostly superficial. Okay? It's mostly superficial. Because the real meaning of, what's the real meaning of K1 delta x? A little bit of change of one of these things, right? A little bit of change of some quantity in the real world. Okay? So if you go into a different coordinate system, like some of you have seen polar coordinates, and there's other kinds of coordinate systems you can choose. Integral doesn't mean area. It's just the fact that we're in rectangular coordinates that these little bits of accumulation incidentally become areas of rectangles. Okay? But in traditional calculus over the years, this has become the focus. Okay? This idea of integral meaning area or area of rectangles has become the focus. Okay, so what about if we make delta x smaller? So we have just shown how I'm showing a smaller delta x, smaller steps. Then what? Then the rectangles will be skinnier, and the tops of those rectangles will do a better job, just like our step function did a better job matching the curve. Now the tops of those rectangles do a better job matching the curve. And so what about the sum of all those rectangles then? It's kind of converging on, if we make delta x very, very small, like dx. So now imagine dx, all right? Dx, as small as you can think of. And so it's like you're like adding up the area of sticks, like an infinite number of sticks across there. And what do you get? So now this is the integral of 1 to 4.1 dx. And we have this kind of geometric meaning as area between the curve and the x-axis. Okay, so as you go into Calc 2 and you're reading textbooks and you're in other courses, there will be an emphasis. You'll see this emphasis of integral is area. Okay, so we want to be aware of that so we can navigate that. All right, so we can look at that and say, okay, they're talking about area, but I know something much bigger than that. I know that what that area, what they're saying, if this integral is area, I know that integral is the amount of accumulation of some quantity, right? It's the amount of accumulation of something like height or volume or weight or work or force or whatever, okay? So this area understanding of integrals is superficial compared to what we've done. Okay, I hope you appreciate that. So I want to go back to that. So let's talk about what if the rate of change was negative. So I'll make a new one down here. So here's our rate curve. Suppose we got like so here's our rate of change curve. Okay, and suppose we want to talk about, so this is R. We want to talk about the integral from 0 to 10 r x dx. So we've got that red rate function. I've got this expression, 0 to 10 r of x dx. What do we understand that to mean? Amount of accumulation, right? That's a value. Based on the rate function that we have, that's an amount of accumulation from 0 to 10. Okay, as x changes from 0 to 10. And what happens is that rate goes negative in terms of, we're summing up bits of accumulation, right? So what's happening to the accumulation through here? It's increasing and then decreasing because the rate is negative. So the net accumulation is going up and then it's going down. And then here it starts to go back up again until we get a total amount of accumulation over that. So when the rate is negative, there's a decreased effect on that total, right? On that total accumulation from 0 to 10. So then thinking about that in terms of area, what would this mean in terms of area? What would this mean in terms of area? Okay. So there's area there, right? So we're talking, it's between the curve and the x-axis. So does that integral from 0 to 10 calculate the sum of those three areas? So when you talk about area can only be a positive value. Area can only be positive. So does it calculate the sum of those three positive areas? No. What does it really? So if we call this area 1, and we call this one area 2. These are all positive values because area is always positive. What would the value of this integral be in terms of those positive values, a1, a2, and a3? a1 minus a2 plus a3. Thinking about our meaning for integral, when the rate is negative, it's going to make the total accumulation go down. So as thinking about it in terms of area, any area that's carved out under the x-axis will have a negative effect to the integral, just like it would have an accumulation, right? A negative rate would mean the accumulation was going down through that x interval. Okay, does it make sense? All right, so let's, what are we going to do? So so we're going to start using web work. So homework is going to be, we're going to use online homework. So the first one is up. So we'll do the first problem together. Okay, one more thing though. I don't know how to spell this. I'm hoping that's how you spell it. Okay. Thank you. My daughter does the spelling, right? Okay, here we go. So our meaning for that thing right down there was that summing up bits of accumulation, right? K delta x plus K delta x plus, that should be delta, sorry. So now we have a new meaning for this, which would be summing up what? Summing up, so this is like height, right? And this is like width, areas of rectangles. So when you see that thing now, the sum of shouldn't be the function, my fault. So this should be individual values of rate found through, so there we go. Okay. So this expression up to this point has been for us summing up bits of accumulation. K delta x plus K delta x plus K delta x. Wow. Okay, we're home. We made it. Okay. So this expression, so K delta x plus K delta x plus K delta x, that's supposed to be an I. I told you it'd be rough today. Okay. So now it also means this summing up areas of rectangles to be, so this would be an approximate accumulation. So this would be an approximate area, or actually now difference of areas, an approximate difference of areas. All the area above the x-axis gets added in. All the area below is subtracted. Okay? So that now has two meanings for us. And this, what this thing is called, which we haven't called it yet, is called a Riemann sum. It's called a Riemann sum. And it's just the same thing we've done. K delta x plus K delta x plus K delta x is called a Riemann sum. So now we have two meanings for it. Two meanings for it. So let's look at web work. Okay, if you go to webwork.asu, I'm not telling you to, but if you were to go to webwork.asu.edu, let me just do that. You see this screen right here, and you're going to go to MAT 270 and click on my name, and it will take you, you may have to log in after this step. After you log in, you'll get to the main page for WebWork. Here's the first assignment. Integral as area, due Wednesday, October 15th. And you see it's due at 1 p.m. What's that? I haven't assigned it yet. Okay, so I just need to click one button and then you'll see it. Okay. So when you click on that assignment, you'll see 7 problems. Let's do the first problem together. Here we go. Okay, so I'm doing your homework. Are you interested? Yes. Okay. All right, here we go. So consider this integral. Find the Riemann sum for this integral using right endpoints and n equals 3. Okay, so up to this point, this has meant an approximate amount of accumulation or an exact amount? Exact amount. They're saying find a Riemann sum. Would that be an approximate amount or exact amount? Approximate. Okay, so we're giving you an expression that's an exact amount of accumulation or an exact difference of areas on the graph. And they're saying use a Riemann sum to make an approximate for that. So I'm going to need to graph this so we can get a good picture. So I'm graphing calculator. Okay, so we can graph 3x squared 4x plus 2. And that function, does it relate, for us, does it relate as a rate of change function or an accumulation function? A rate of change function. That's our meaning for it, okay? So I'm going to graph that, and we're looking between, what, x equals 1 and x equals 4. And they want us to use a Riemann sum, right endpoints of each interval, and 3 intervals. So this is nice and easy. What will the width of each interval be? We're going from 1 to 4 with 3 intervals. So that's real easy. So here's that graph and get a better view of it. Too much. Need to do this. There we go. So you told me there's 3 intervals from 1 to 4. So here's 1. So that's 2. There's our first interval. There's 3. There's 4, our third interval. And so we're going to use what? For each interval, they're telling us to use the right endpoint, which is the same thing as our right function, our right approach, meaning we're going to take that function value to be constant. This is using right approach, right? Review. And before we saw this as a step function that's going to allow us to calculate accumulation, but in this alternate understanding, we're seeing these as rectangles. The Riemann sum then is going to be an approximate either amount of accumulation or in this case an approximate area. Okay? Will our approximate be too big or too small? Too big. Obviously too big. So how are we going to do this? This delta x is 1. Delta x is 1. How are we going to get the heights of these rectangles? How are we going to get the heights of these rectangles? So how do we find the height of this rectangle? We're going to plug in, just like we did before, we're going to plug in the x value at the right side into our, what used to be a rate function, now it's just any generic function. We're going to plug 2 in. And I should have defined a function instead, but I'll do that quick. Here we go. So you do f of x, and y equals f of x. Make sure it gets graphed. There's the graph, and now I can come down here and just do what? F of what? For the height of the first rectangle. F of 2. Now it just found, oh, I don't like that. Got it. Okay, so I just put 2 into this function, and it told me what the y value was, and that's the y value at the right side of the first interval, and then the whole first interval. So what is the area of this first rectangle? It's going to be 20 f of 2, the height from the right side, times delta x, which is 1, which is 22. Okay, how am I going to get the height of this second rectangle? I'm going to do f of 3. F of 3 will be the height for that whole rectangle. 41. What's my width? Second area is? It's going to be f. This is going to be f of 3 times 1 equals 41. Finally, f of 4, 66. 66 times 1. Why times 1? If you have a different delta x, you're not going to multiply by 1. If your delta x is different, so it's what? It's height times width. So what is this Riemann sum? This was 66. So this Riemann sum trying to approximate the area between that red curve is going to be 22 plus 41 plus 66 equals 129. Did I do it right? I'm not good at math. Hold on, let's see. Okay, here we go. 129. Now notice you have limited attempts. So on the ones with more than one blank, you get 7 attempts. So if you've done 4 and 5 attempts, stop. Don't just keep guessing. Okay? You can get help by emailing me and sending me a note, but be specific. But use this button at the bottom of the page where you're having trouble, because I get a direct link to your problem. Okay? You guys are going to have different numbers, right? So this is the beauty of the online system. You won't have this exact problem, but it'll be like it. Okay? So I'm going to submit 129. And maybe correct. So what you're going for is, when we get the second part correct, that'll be green too, and you'll get this green bar. Okay, you'll get right underneath this feedback table, you'll get the green bar. When you get the green bar, you don't have to do anything else. Your correct answer and points were just saved once you get the green bar. But there's partial credit also. You don't have to email me and say, I would like to submit my answer for number 5 now. Okay? Once it's all electronic. Once you get the answer in, whether it's partial or the full problem, you get total credit.
By leaving it blank and if we're getting it wrong, you just use an attempt?
Yes. Yeah, so if there are multiple boxes that you're filling out, try to do as many of them as you can before you attempt. Don't do one, like don't do this. Don't do one and attempt, and then do the next one and attempt, because you're using up your attempts. So answer as many as you can before you make each attempt. Yeah?
Do you lose points for using attempts?
No. If you get it all right on the 7th try, you get the same credit as on the first try. Other questions about the system? Okay, so then look, what's part B? It's the same question, but use the left endpoints. We know how to do it. So this is just taking everything we've learned already about accumulation and finding the height of the steps, and just taking more a geometric approach of finding areas of rectangles. Everything else should feel parallel.
Is that what's going to superficial calculus side?
What's that?
Is this how it's going to be from now on? Doing it?
No, it's always going to be about quantities in this class. Yeah. Okay, so let's do cards.
Could you go back to that graphic really quick?
Yeah. I don't have the writing now. Okay, please take it seriously.